For this lesson, we're going to be looking at mutually exclusive events. So, to get started, let's briefly recall the law of inclusion and exclusion. And this is really how we determine all of those numbers in Venn diagrams using this law. So, the number of ways A or B could happen is equal to the number of ways A can happen plus the number of ways B can happen minus the number of ways A and B can happen. Now, what we're doing with this subtraction here is we are removing the double counting. Just like we do with our Venn diagrams, right? So for example, when we have our Venn diagram that looks like this, when we're looking for A and B, we first have to add everything in A, then we add everything in B. But if you notice, I accidentally highlighted that middle bit 2 times. I highlighted it once when I highlighted the A part green, and then I highlighted it a second time when I highlighted the pink part. So we've accidentally counted this 2 times. Therefore, we have to subtract it. So that's what this subtraction piece over here is all about. So now what we can do here with this law is we can actually just divide both sides by S. So if I divide this side by the number of elements in my sample space, and if I divide this side by the number of elements in my sample space, what I am left with is the following equation. I'm left with the addition rule for mutually exclusive events. So this is, this should say for non-mutually exclusive events, right? Because they have this overlap, they are non-mutually exclusive events, which means they can be occurring at the same time. So 2 events are mutually exclusive if they cannot both occur at the same time. In other words, there's no common events between them, and the probability of A and B is 0. So if they are mutually exclusive, they cannot occur at the same time, and this middle bit here has no elements in it. It's 0. So when I go to subtract it, I'm subtracting 0. So no issues here. So this here is an example of non-mutually exclusive. And if I had a situation like this, where they're entirely separate, then these would be mutually exclusive. So if we have events that are mutually exclusive, so I apologize for the typo here, this should say mutually exclusive, then my probability of A or B is just equal to the probability of A plus the probability of B. And again, that's because when we subtract the probability of A or B, we're just subtracting 0. So we don't need to write that. And this is because there's no overlap there, right? There's no overlap, so I can just take the probabilities of both and add them together. So let's do some examples with this. This first one here, the Cookie Monster's cookie jar contains 5 chocolate chip, 4 Oreo, and 7 Fudgio cookies. If he takes 1 cookie, determine the probability that it is Fudgio. So first I'm going to start by defining my event. So event A would be that we choose a Fudgio. Now our probability of event A would be the number of ways we can choose A divided by the total number of elements in our sample space. So if I look at the question, there are 7 Fudgio cookies, and our total number of cookies in the jar are 5 plus 4 plus 7, which is 16 total cookies. So our probability of choosing a Fudgio is 7 divided by 16. Now let's find the probability of choosing an Oreo. So event B, choosing an Oreo. So we'll calculate it in a similar way. Our probability of event B is the number of ways B can happen divided by our total number of outcomes. So if I look at the question, there are 4 Oreo cookies out of the 16 total cookies, and this one we can reduce a bit to 1/4. So we always reduce it where we can. Okay, now for C. We want to determine the probability that the randomly chosen cookie is a Fudgio or an Oreo. So when we have this word or, we need to think to ourselves, are these mutually exclusive events? Can I simultaneously choose a Fudgio and an Oreo? No, I can't simultaneously have a cookie that is both a Fudgio and an Oreo. It has to be a Fudgio or an Oreo. So these are mutually exclusive. So that means we can just add them. So that means our probability of A or B will be the probability of A plus the probability of B. And again, that's just because the two of them can't occur at the same time. Therefore, if I subtracted anything else, it would just be 0. So we'll have 7 over 16 plus 4 over 16. I'm just going to use the ones with both 16 as the denominator so that we can just add right away. And that will give us 11 out of 16. There we go. So let's try a slightly different example. Yet again, another one with some dice choices. So in the toss of 2 dice, determine the following probabilities. So because we're looking at 2 dice, we'll quickly sketch out our dice chart. So we have 1, 2, 3, 4, 5, and 6. Just to give us a little bit of a visual. 1, 2, 3, 4, 5, and 6. There we go. And we'll write out all of our outcomes here. Okay, so we're looking for the probability of rolling doubles here, which is pretty easy to find now that I have all of my outcomes all laid out. So my probability of doubles, I'll look to see how many doubles we have here. So how many doubles do I have? 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So I have 1, 2, 3, 4, 5, 6 doubles out of the 36 options, and that simplifies to 1/6. Now for a sum of 6, so I'm going to look through and find all of my sums of 6. So I have 1, 2, 3, 4, 5 different sums of 6. So my probability, sum of 6, we have 1, 2, 3, 4, 5 of them out of the 36 options. Okay, So for C, we're being asked to find the probability of doubles or a sum of 6. So this word or is telling us we need to determine, are these mutually exclusive? So are they mutually exclusive? No, these are non-mutually exclusive. I'll show you why. Exclusive. And this is because of this right here. In the middle, we can simultaneously have doubles, a 3 and a 3, as well as a sum of 6. So at the same time, we can have doubles and a sum of 6. So these are not mutually exclusive. So I'm just going to do the calculation for this down here, just so we have a little bit more room. So our probability of doubles or a sum of 6, that will be equal to the probability of doubles plus my probability of a sum of 6 minus the probability of doubles and a sum of 6. Now we have to subtract it because we count this middle one right here. We counted it once over here and we counted it again over there. So when we add those, we actually double count that middle one right here, that outcome. So our probability of doubles was 6 over 36. Again, I'm going to keep the 36 in there just so that I don't have to worry about common denominators. Plus 5 out of 36 minus the probability of 2 of them happening. Now to determine that, I look at how many ways they're both simultaneously happening. There's only 1 out of 36 that is both a double and a sum of 6. So that will equal 10 out of 36, which reduces to 5 out of 18. So we just have to be very, very careful not to double count. That's really what all of this comes down to. So let's try another one, something a little different. So in this one, 1,000 Aurora High School students were polled to see their TV preferences with the following results. 350 students watch Big Bang Theory, 650 students watch Modern Family, and 230 watch both. So the first thing that we need to do is we need to draw a Venn diagram to illustrate the above events. So we've done that a few times. So I'll draw my Venn diagram quickly. Go. It's not perfect, but that's okay. Okay, and I need my 2 circles on the inside. So there is 1 circle. And we'll need a second one. There we go. Perfect. So our 2 circles, we're looking for those who watch the Big Bang Theory and those who are watching Modern Family. Okay, so when we work with our Venn diagrams, the first thing that we do is we'll state our sample space if we have it. So here we know we have 1,000 students. Now we always start with the middle. So we know that 230 watch both. So now what we're going to do is we are going to ensure that we're not double counting. So for the Big Bang Theory, we have that 350 students watch, but we've already counted those 230 students in the middle, so we have to subtract them. This leaves us with 120. Similarly, for Modern Family, we are told that 650 students watch Modern Family, but we've already counted 230 in the middle there, so we don't want to count them again. So we subtract, and that leaves us with 420. Just like that. Now, of course, we also need to determine how many people watch none of them. We also need to account for that. So for our neither category, we will take our total minus those who watch just Big Bang Theory, minus those who watch just Modern Family, and minus those who watch both. And that will leave us with 230 students. So we'll just put that over here outside of those circles. So now we have some probabilities to determine. The first one is that a student watched Big Bang Theory and Modern Family. So if they watch Big Bang Theory and Modern Family, that will be this middle bit right here. So Big Bang and Modern Family, this middle bit right here. So our probability of Big Bang and Modern Family will be 230 students out of 1,000, which will give us 0.23 or 23%. So that's our middle bit there. The ones who are watching Big Bang Theory and Modern Family. Now, what about the probability that a student watches Big Bang or Modern Family? So in this case, we want to take all of those students. So it's or. So they could just watch Big Bang, 120. They could just watch Modern Family, or they could watch both. Now in this case, even though these are not mutually exclusive, right? They're not mutually exclusive because we have the middle part. Because we already subtracted when we were making the Venn diagram, we are not double counting. We're not double counting because we actually took the time to subtract already when we made the Venn diagram. So in this particular case, we do not have to subtract, and it will give us 770 all over 1,000. Oops, forgot a zero there. Sorry about that. And that gives us 77%. So just be mindful that if you have already subtracted because you made the Venn diagram, you don't need to do it again. We don't want to subtract more than we should. Okay, let's try another one, something a little different. Tommy loves Kit Kat bars and Aero bars. While trick-or-treating on Halloween, his neighbor randomly picks out one chocolate bar from a bowl of 100 bars. The bowl contains 24 Aero bars, 27 Coffee Crisp bars, 20 Kit Kat bars, and 29 boxes of Smarties. What is the probability that Tommy will get one of the chocolate bars he likes best? So we want to determine the probability of getting an Aero or a Kit Kat because those are the two that Tommy likes. So are these mutually exclusive? Can I simultaneously have a Kit Kat and an Aero bar if I only get one bar? So if I only pick one bar randomly, can I simultaneously have it be a Kit Kat and an Aero? No. So what this means is that these are mutually exclusive. So let's define our events. So event A would be that we get a Kit Kat, just like that. And event B will be that we get an Aero bar. Now, because these are mutually exclusive, to find the probability of Tommy getting a Kit Kat or an Aero bar, we can just add them. Again, because we cannot simultaneously have a Kit Kat and an Aero bar at the same time if I only picked one chocolate. So the probability of getting a Kit Kat, there are 20 Kit Kat bars out of the 100 bars, plus 24 Aero bars out of the 100 bars. So that will give us 44 out of 100, which is 44%. There we go. So no double counting going on because we cannot simultaneously have both. Okay, last one. Heather owns 16 tops. There are 11 t-shirts, 3 of which are red, 5 tank tops, 1 of which is red. What is the probability that you will see Heather in a tank top or a red top if she randomly picks a top from her closet? Okay, so let's define our events first, and then we'll determine if they're mutually exclusive. So, what's the probability that Heather will pick a tank top or a red top? So, event A is that she picks a tank top, and event B is that she picks a red top. All right, are these mutually exclusive? Could Heather be simultaneously wearing a tank top and a red top at the same time? Absolutely, because she has a red tank top. So she could simultaneously be wearing a red shirt that is also a tank top. Those can happen at the same time. So these are not mutually exclusive. So that means that if I just added them, I would accidentally account for the red tank top when I counted the tank tops, and then I would accidentally count it again when I counted the red shirts. And we don't want to do that. We don't want to double count. So our probability of A or B will be our probability of A plus the probability of B minus the probability of A and B, because we don't want to double count that red tank top. So probability of a tank top, there are 5 tank tops out of the 16 tops. Then probability of a red shirt, there are 4 red shirts. There's 3 here and 1 here out of the 16. And then we want to subtract any double counting, and it's that single red tank top that's accidentally getting counted twice. So that will give us 8 out of 16, which is 50%. And there we go.